Alrighty, so now we're going to talk about entropy. And I guess we should just start with, well, what is entropy? And it's kind of hard to define, like energy and other things. We might talk about exergy at some point. It's kind of just like a quantity that we define that's useful in some contexts. But if you want to get like an intuitive idea, some people say it's kind of like a measure of the disorder. We talked earlier about how there's a number of permutations or different setups a certain thing can have, and the more setups it has, the more likely it is. It could also be like how many possible kind of states there are. So like how many. So we talked about this kind of like with the bell curve, right? And in fact, you can kind of write entropy as a function of how many states there are and like their probability. So there's something called the Boltzmann relation, which is like the entropy. Capital S is entropy is equal to like the Boltzmann constant times the log of W, which is like basically the probability of a certain state. Or a more advanced one is you kind of add up basically the probability of each setup. That way they can be like if it's a non-uniform probability essentially. So these are some ideas about what entropy is. There's also ways to generate it. So whenever you have an irreversibility, entropy is going to increase because there's more possible states. So like when you convert work into heat, you're going to generate entropy because now this heat can be distributed more randomly. There's more possible states and you can't go back. There's also things like friction, unrestrained expansion, and all those are going to increase our entropy. There's also heat distribution or heat transfer. We'll talk about that in a second. But this is kind of what entropy is. And so now that we have a general intuition, we can kind of get to the more rigorous definition of like what it is and how we can use numbers and stuff. So we're going to go ahead and start by looking at this setup right here. You can see we've got a heat reservoir right here. It's bringing in a differential amount of heat from the reservoir to our reversible heat engine. Then we've got a work output that's reversible. And then we've got work into this piston cylinder system at some temperature T. And then this also has a work output from the system. So we go ahead and we say that basically the whole combined work of our system is WC, and we do like an energy balance on this thing, right? What we're going to have is that basically our like a differential amount of work combined is equal to the summation of our reversible plus our system work. And this is going to equal the heat coming in if our system is this red box basically, so it includes this heat engine and this system. So we'll have our delta Q from the reservoir minus a dE combined. So this is a way of writing this. If you'd imagine, like a more common way I might write this, as we've seen before, is like a differential amount of change of the energy is equal to our work added plus the heat done. This would be negative because both of these are actually work done from the system, which would decrease the energy. And so if you go ahead and you add this across and you subtract this across, you'll get the same thing as we have above, right? And we also know that we have a reversible heat engine, which means that the ratio of the temperatures has to equal the ratio of the heats. So we have T over TR has to equal our Q. Come on, Q, differential Q over differential Q from the reservoir. Okay, and if we solve this for our dqr, what we would get is that this equals multiply across, right? We have a dq times tr over t. So now if we plug this in up here, what we would have is that the work output has to equal our dq, where before we had dqr, which is this, and now we have this, times our tr over t. And the point here is that our dqr is always going to be constant, and the same with the TR, because we're basically drawing the same amount of heat. But this dq and this T are actually variables because it's going to change, right? As this piston gets more and more hot, it's going to increase in temperature, and we're going to have less heat being transferred, and we also have a minus dE C right here. And so now what we're going to do is we're going to let this whole thing be integrated across the cycle. So if we integrate this whole thing across the cycle, what we'd have is that the work output from this combined system has to equal integration. This circle here just means we start and end in the same place. We have a dq tr over t, and then this dE is going to go to 0 because energy is a property, and so if we start and end with the same state, then our properties have to be the same, which means that there's going to be no net dE. We also know that this tr is constant, so we go ahead and pull this out. we would have that this is equal to TR loop integral over dq over t. And now if you think back to our statements of the second law, we basically have a device that's just taking heat from a reservoir and pumping out work, which can exist, which means that the work output we get has to be less than or equal to 0. So we can go ahead and we can divide over this TR, and we get that the final expression is that our loop integral of dq over t has to be less than or equal to 0, less than or equal to 0. And this is true for any process. This is basically one of our statements of the second law. But specifically for a completely internally reversible process, so there's no irreversibilities inside of our system here, so there's no like friction or unrestrained expansion or anything like that, we know that this also has to work in the reverse direction. So if you'd imagine if our dq is a positive quantity, then it would not be less than or equal to 0. But if our dq was a negative quantity, basically, I mean this whole integral, so as you add up the net heat interaction, it's negative, then it would work in this direction. But when we reverse it, it would be positive, which means that it would no longer work. And remember that this relation holds for any process. So when we reverse it, this still has to be less than or equal to 0, which means that if we're talking about a reversible process, the only way this can work is if it's the special case where it is equal to 0. Equal to 0. And now think about this for a second. We're integrating up some quantity over a full loop, which means we start and end with the same state, and it's equal to 0, which means that this quantity basically doesn't change as we integrate, starting somewhere and ending at that same spot, which means that it's defined by the state that it's in. If you remember from earlier, we had this DEC, and we said that, hey, since we're starting and ending with the same state, then our net change in energy is going to be 0. And here we're seeing that our net change of this quantity right here is 0. And therefore, we can say that this has to be some kind of property of our system. And you want to guess what that property is? It's entropy. Yay! So our definition is basically that some differential slice of entropy, capital S, let's put like some bars or something here, equals a differential amount of heat divided by the boundary temperature for an internally reversible process. And so if you want to get the delta S, you just add up from state 1 to state 2, your differential Q's over your boundary temperature, internally reversible, right? Reversible. But now the question is, but what if I don't have a reversible process, right? How can I use entropy from its definition here if it's internally reversible? But obviously real processes, there's no real process that's reversible. There's always something like heat generation or friction or something. It's never perfect. Well, what we can do is we can come back to this integral right here, because I told you this works for all processes. And what we're going to do is we're going to say, all right, so what if I start at 1, I go to 2, and I go back to 1? And from 2 to 1, I'll have an internally reversible process. But from 1 to 2, this doesn't have to be reversible. It can be, irreversible. It can be generating entropy all over the place. So you know that a closed loop integral of the heat transfer to our system divided by the boundary temperature that it's coming at has to be less than or equal to 0. So we can break this up into from 1 to 2 and then back to 2 to 1, right? So we'd have an integral from 1 to 2 of our dq over t plus the integral from 2 to 1 of our dq over t has to be less than or equal to 0. And now this is our internally reversible process. So I know that this is actually the same thing as S1 minus S2. Remember, because our 1 is where we're stopping. And so now if I subtract this over to the other side, I would get S2 minus S1, which is the same thing as delta S. And then if I relook at my inequality right here, I'd have delta S, delta S is greater than or equal to integral from 1 to 2 of our dq over t. And this is basically just the integral of our not necessarily reversible process, right? This could be irreversible. And now another way we could write this is that we could say, well, our delta S has to at least equal this 1 to 2 over dq over t, right? But now we need to add some other quantity for entropy that represents how much it's greater. And we call this Sgen because it's the generated entropy. Basically, the difference between the irreversible process, which would just be this integral, and the real process change in entropy is our generated entropy, which there's always going to be generated entropy. I talked about this earlier, things like friction, understand expansion, heat transfer over a finite temperature difference. I can go ahead and talk about that a little bit more. So basically, if you imagine if you got like a hot thing, maybe this is like a neutral thing, neutral, neutral, and then we've got cold. When I bring heat across here, I've basically brought energy from here to here, and we're assuming it's something called a finite temperature difference, which basically is just like we know that the temperature is happening across. The only way for me to bring heat from this neutral temperature back to hot because it's a lower temperature would be to add energy, right? So there's no way for me to get it back without adding energy, which means it's irreversible. And you can imagine the only thing I can do without adding energy is basically just cascading this down to lower and lower temperatures. So whenever you bring heat from a higher temperature to a lower temperature, you're generating entropy. All right. So this is how you do it for any old process. And entropy is also one of our properties that we've talked about. Specifically, if you want to talk about like the intensive and independent. Intensive means it's independent of mass, so we'd want to use lowercase s, which is our entropy. Why is it not working? Come on. Entropy per unit mass, okay? And we could do the same thing with our diagram right here. If you remember before, we had a TV diagram. This is a TS diagram. It looked exactly the same. And you could find things like our S, if you know quality. That's an integral symbol. Come on. S equals basically the S at the saturated liquid state plus our quality is the ratio we've gone across here. If we're looking at a saturated mixture times SFG. I don't know if I used this notation before. This is equal to SG minus SF. It's just a different way of stating it. And so if you have two properties, this could be one of your properties. You can use lookups and things to find your entropy. This would also mean that, you know, if you want to find the delta S, big delta S, all you'd have to do is find your mass of the system times your specific delta S. So if you want to use lookups and things like that, this is how you do it for entropy. And now we're going to look at some more equations that you could use for solving entropy type things. These are really useful. We'll see once we start getting to like the gas power plant, we're going to be using these all the time. And so where it's going to start out is we're going to look at kind of an idealized system. So the system we're going to look at is going to be stationary. Maybe I'll write these down. So it's stationary, and the process is reversible. And I think those are the two assumptions. Yep. Stationary closed system with internally reversible processes. All right, so we know that the heat added a differential amount of heat. We're looking at basically a differential relation because we're going to integrate this up at some point. Minus the differential amount of work done by the system has to equal differential amount of change U. The reason we don't have a KE or a PE is because we're assuming it's stationary. So relative to whatever our reference point is, it's not moving, which means that we can't have a change in kinetic or potential energy because both of those require it to be moving. Okay, so now what we're going to do is we're going to rewrite this delta Q as T ds, because if you remember, our ds is a delta Q over T for an internally reversible process. So if we just multiply this over, we can break open our dq here. And now our work, because we're looking at a reversible process, we can't have work that basically generates heat. So if you've imagined something like a spinning something inside, like if you imagine this is like a mixer, right? And it's mixing things up and it's basically turning this ordered rotational work into more chaotic energy, basically. Things like that aren't going to work because that's not an internally reversible process. So the work interaction for an internally reversible process has to be able to be reduced to basically just force acting across a distance, across our boundary, which we're going to rewrite as P dV because pressure and volume are things that we know. P dV, this has to equal our du. Now, what we can do is we can substitute in enthalpy if you remember the definition of enthalpy, is our P, come on, or I guess we should probably start with U. Normally it's written as U plus P times V. And so a differential H is going to be a differential U plus, and then we do the product rule here and we'll have a P, come on, dV plus V dP. And if you notice, this right here is the same as these two terms right here. So if I go ahead and I write out, here we'll go ahead and rewrite this top one real quick as, the color is going to work today, TdS equals du plus P dV. Okay. And now this du plus P dV, we already know this, but we could replace it with dH minus this term, and that's exactly what we're going to do. So we can call this equation 1. It's called the Gibbs equation, I think, if you want to look into it more. And then our equation 2 would be T ds equals our dH minus V dP. And I forgot to mention, but these obviously they work for per unit mass as well, which is usually what's going to be easier to look at for looking at our states, right, and lookups and things like that. So we're just going to rewrite this as lowercase s per unit. Basically, we just divide everything through by mass. So per unit mass, lowercase s, lowercase u, lowercase, this would be v, and this would also be a lowercase s. And then if you want to, you could divide everything through by t, and you'd solve this for a ds. Now to see if these equations become useful, there's really two different setups that we have. The first setup we have is for solids and liquids. So if you remember, for our solids and our liquids, we assume that it's incompressible, which means that the specific volume doesn't change, right? If I give it a ton of pressure, it's not going to get compressed very much. It's just, we're assuming it's constant specific volume, which also means that our CV and our CP are the same. We just have one specific heat called C, all right? So that means if, let's just say we look at the first equation, right? It's like TdS equals du plus P dV. Well, we can't have a differential volume, so this is just going to go away. Boom, off the bat. If we want to solve for a slice of entropy, this would be du over T. But if you remember, our C is the same thing as du over dt. Yes. So we would multiply the dt over, and this du is equivalent to a C dt. So we just have C dt over T. And if we want to get the change in entropy based on state information we have, then we would just add this up. So we'd integrate from state 1 to state 2. C is technically a function of temperature. And then we'd have a dt over T just like this. And at this point, this is where you'd probably make the constant specific heats assumption. So it's pretty accurate for solids and liquids. So basically, if we assume that it's constant across temperature, then we could just pull this out. If we evaluate this integral, we get C natural log of T2 over T1. And then in the special case of an isentropic process, we would have this set equal to 0, which means that our 0 is equal to C natural log T2 over T1. We can divide through by the C, it goes away. If we raise e to the power of both sides, then we get that 1 equals T2 over T1, or that T2 has to equal T1. So isentropic, which means constant entropy, is the same thing as isothermal for an incompressible substance, which is our approximation of solids and liquids. Now for gases, it gets a little bit more complicated. The two equations that we're going to be able to pull in, or I guess technically three, depending on how you look at it. Our first is the ideal gas law. So PV equals RT. Hello, RT. That's our first thing. And then our second thing is our specific heat. So we have the constant pressure specific heat. It's delta H over delta T. And we also know that the constant volume is delta U over delta T. So let's first take a look at the first equation we had. So the first equation we had was TdS equals du plus P dV. Okay? So now what we're going to do is we're going to divide everything through by t. We're going to replace this du with a cv delta t. So we'll have a ds equals cv delta t divided by t. And then for this term right here, we're going to plug in the ideal gas law. So we're going to have p over t out front right here, which if we go ahead and we divide over this t, we can say that's the same thing as r over v. So if I go ahead and I just like do this, p over t, same thing as r over v, just by multiplying and dividing across things. So we can go and replace this with the r over v, and then we'll also have a dv, so I'm just going ahead and keep all the dv terms by themselves. So we'll just write this as r dv over v. And then for the second equation, what we would have is our TdS. TdS, is it going to load? Right, equals our dH minus, and then it was VdP, I believe. Let me double check this. And then we're basically going to do the same thing. We're just going to plug in the same two equations to simplify this. Yes, it was minus VdP. Okay, so we'll get that our ds equals, this time we're dealing with enthalpy, so we'll have a Cp delta T over T minus this time. And now notice that we'll have V over T. So if we come up to our ideal gas law, V over T is the same thing as R over P. So I'll go ahead and write this as R times a dP over P. Okay, and now we have our two equations right here. We can go ahead and we can integrate these up, and we can get the change in entropy. And we're going to have the same problem as last time, though. So we can integrate this just fine. This is going to give me an R natural log of V2 over V1. And then same thing right here, except it'll be negative, and we'll do P2 over P1, right? But for these integrals right here, we have the same problem of the specific heats. For gases, we can do the constant specific heat thing again, but it's not as accurate. And so sometimes what you'll see is you'll see tables of what's called like this S degree function, which is basically just someone evaluating the integral from 0 to t of, I want to say it's Cp, it might be the other one though, delta t over t. And so basically if you want to get your delta S, you just need to do like S degree 2 minus S degree 1. And this would be basically in a table for different temperature values for your gas. You would just look this up. And then I think there's another one that would do this one as well. But we're going to look at the constant specific heats one just because that's kind of what's emphasized more in the problems that we do. So if you go ahead and you do integration on both of these, you'll get two equations. The first one is going to look like, you'll have your CV, natural log of, wow, saving is being really annoying today, T1, and then you'll add your R natural log of V2 over V1, and then 2, hello, and these are both equal to delta S. I guess I should put that up front. This is delta S. 1 and then 2 is our delta S is Cp natural log of T2 over T1, and then this one will be minus R natural log of P2 over P1. So boom, you got your P2, P1, T2. You can figure out the delta S. In the case of isentropic, you would set these equal to 0. And basically what you would do, I'm not going to go through the whole thing right here, but just to give the rundown of what you would do. You would add 1 over, and you would divide it across. So basically you'd have a natural log of something on one side equals some constant out front, natural log of the other thing. And then you'd use the power rule. So because it's multiplied up front, I could bring this into the power. Then I would raise e to both sides to cancel out these natural logs. And what you would get is two different equations for the isentropic case, and these are going to be very handy. You want to keep these in your back pocket once we get to the gas power plants. So the first one, let me go ahead and see, I have these written down, is that, so for the isentropic case, isentropic, we have that the ratio of our temperatures, so T2 over T1, is equal to V1 over V2, V2, V2 to the power of K minus 1. And then for the other one, you'll have the same thing, T2 over T1 is equal to P2 over P1, this time to the power of K minus 1 over K. And now if you set these two equations equal to each other, you get one more equation that's going to relate the pressure ratio. So our P2 over P1 equals our V2 over V1, all raised to the power of K. And now we talked about this earlier, but K is the ratio of our specific heats. So real quick, this just kind of simplifies things so you can get that R out of the equation. So your K is the ratio of the specific heats. It's Cp over Cv. And then also by combining the definition of enthalpy and the ideal gas law, or the specific heats and the ideal gas law and the definition of enthalpy, I think. I have this in a different video. But you can find that R plus your Cv equals Cp. And if you use these two equations, it'll clean this up into this nice power of K minus 1 form. So make sure you have these equations remembered, ready to go or something, because they're going to come up later. Definitely make sure you have those down. So now we're going to talk about entropy balance. The idea with entropy balance is it's similar to the energy balance equations that we had earlier. So if you remember, like the Q minus W equals delta U plus delta KE plus all of that, we're going to have that for entropy as well. So for the open system, I guess we just start with the closed system since it'll be a little bit simpler. The ways that we can change our entropy are first by heat transfer. So all of the, added up, all of the heat transfers that we have divided by the temperature at the boundary that they happen at, plus just the entropy generation that we get during the process. Now for the open system, we also have entropy from mass transfer. So we're going to have that the rate of change of our entropy with respect to time is going to be adding up. First, we'll still have our heat transfer rate form divided by the boundary temperatures. But now we will have to add up all of the mass flow rates at the inlet times the specific entropy at the inlet, and subtract the mass flow rates at the exit times the specific entropy at the exit. Because if you remember, mass times specific entropy gives us total entropy. M dot will give us entropy per unit time. And then we'll also have to add in our SGen in rate form. And just like we did with earlier, if you want to, you can also write this in terms of like your delta S equals, and then you'd multiply these each by your time step, or you could do it per unit mass. So that may be a little bit easier, right? So your delta S per unit mass for an open system would just be the sum of Q over temperature per unit mass. That's why it's a lowercase q. And then plus your SGen per unit mass. And the reason that you don't have your mass flow is if you think about this, transferring mass isn't going to change the entropy or even the energy per unit mass. The way I like to think about this is if you have like some blob of, this is your system and it's a bunch of mass, right? And let's say I send in a blob of mass, or I send out a blob of mass. The way you can think about specific entropy or specific heat, not specific heat, heat per unit mass, right? This right here, this lowercase q, is the energy, right? Averaged across all of the mass. So we take the total heat or the total entropy divided by the total mass, and that's going to give us basically the average entropy or whatever else you have. So If it's very well mixed, decreasing or basically decreasing your energy by moving mass out or in isn't going to change it. You could think about this like, let's say I'm trying to make Kool-Aid, right? Or like lemonade or something. So I fill a tank with water and then I got a bunch of like random powder, right? If I just take out a chunk of this, it's going to change the mixture, right? If I took out a chunk of this, it would change the mixture as well. But if it was really well mixed and I just had, like it evenly distributed, then taking a chunk out of it isn't going to change the average mixture. And same thing if I added in something that had the same mixture, it wouldn't do that. So if we assume that it's well mixed and it's homogeneous, which means basically that there's no like random clumps that have more energy or entropy or something like that, then mass transfer isn't going to change my entropy per unit mass. And real quick, just to finish up, we're going to talk about the isentropic efficiencies. So earlier we talked about the efficiencies of things like our heat engine and our heat pump and our refrigerator and all of that. But we also can have efficiencies for things like the compressor, if you remember, and even the nozzle and things like that. So we'll go ahead and start with the turbine. So basically, when it's isentropic, there's no irreversibilities, right? The entropy stays the same. There's no entropy generation. That's the best case we could have because entropy is a measure of the irreversibilities you have in your system. So the isentropic efficiency of our turbine is equal to the work output we can get in the isentropic case divided by the work output we actually get. So the work output we actually get should always be less than this right here, which means that this quantity should always be less than 1, right? Because this will be something like 2, and this will be something like 1. I actually have these backwards. This should be the other way around because this should always be between 0 and 1, essentially. So how much do we actually get divided by how much could we possibly get in the best case? So if you imagine our turbine right here, we're going to have an outlet state 2 and an inlet state 1, and there's going to be a P2, and there's going to be a P1 that this turbine's operating between, and even in the isentropic case, it's going to be the same. But what won't be the same is our T1, or our T1 will be the same too. But the outlet basically will change depending on the process, right? So for the turbine, in the isentropic case, we're going to have a lower output temperature than the real case because the isentropic case is going to be able to extract more work. So we'll have a T2 actual and a T2 ideal. All right. And so if we go ahead and we neglect our kinetic and potential energy, which is usually something we'll do for the turbine, the work output, we think about this, negative work is equal to our H2 minus our H1. So this will equal basically H1 minus our H2 actual divided by H1 minus our H2 ideal, which we can get from pressure and temperature. Or if they give us an efficiency and they ask for the outlet temperature, it's just a relation that we have and it's pretty useful. Now the compressor is going to be the other way, right? Because for the compressor, essentially what we have is a setup where we have a work input because we're compressing it. So we'll have a P1 and a T1, then we'll have the outlet, and same setup, we'll have the same pressure coming out because we're operating between these two pressures, but we'll have T2 actual and a T2 ideal. So in this case, T2 actual is going to be higher than T2 ideal because in a compressor, you don't want to heat it up more than you have to. That's basically wasted work. So the isentropic efficiency here for a compressor, this one is equal to the ideal input of work over the actual because the actual is always going to be more than the ideal, right? We don't want to have to put in that much work, but in the real world, we're going to have to put in more work than we would in the idealized case. So this is going to equal like H1 minus H2S. Hello, is it going to load? All over H1 minus H2A. So these are the two main isentropic efficiencies. But real quick, I'll just go ahead and give you the bonus for the nozzle. because why not? So if you have your nozzle, right, what we really care about is the ratio of the velocities coming in and out, right? So basically, if you got it coming out faster, then it's doing better. So the isentropic efficiency for the nozzle is equal to the velocity of the outlet. Ideally, no, this is actually, because our actual velocity outlet is going to be slightly lower, squared divided by V2 ideal squared. And the reason we square it is because it's going to relate a lot easier to the kinetic energy, and it's going to simplify better with basically our energy analysis.